So last class we were talking about fins that are extended surfaces, right? That help us to enhance the convective heat transfer. That's the main objective of adding a fin to an electronic, for example, right? So by attaching these extended surfaces, we expect that the temperature of the device will decrease, right? That's why do we add them. And that's pretty common, again, in the electronic industry. So it results that sometimes at certain conditions, the heat transfer is retarded by fins. So not always is useful to add fins. So how this happen? Well, it's similar to what we have been discussing when convection and is competing, right? So adding fins will increase the surface area, then the convective resistance decreases, but the conductive resistance increases because the heat must flow through the solid before being convected through the surface, right? So again, we have this competition, right? And then we need to find a parameter that can help us to determine if a fin should be added or not. And that parameter is the fin effectiveness, that is this big N, okay? So the fin effectiveness is a parameter that is going to help us to determine if adding a fin is beneficial or not. Because again, we have this competition between conduction and convection, the two major heat transfer modes that are occurring in a fin or extended surface, right? Let's look at the effectiveness equation that is in your next slide. So this equation is something that I would like that you take note, please, because we are going to solve a problem to determine the fin effectiveness and decide if the fin should be added or not. So the fin effectiveness can be calculated by the square root of the perimeter times the thermal conductivity divided by the convective heat transfer coefficient times the area, tangent hyperbolic of the fin parameter M that we discussed at last class, right? Multiplied by the fin height. If the effectiveness is bigger than 1, adding fin enhances the heat transfer. If it's equal to 1, adding fin has no effect. And if it's less than 1, adding fins impedes the heat transfer. So that will help us to make a decision if that is the case, if an extended surfaces or a fin is beneficial to add in our system. Again, if you can see from the formula of the effectiveness, right, we are comparing in the numerator and the denominator conduction versus convection, right? We have the K and the H there that are characteristic of these two heat transfer modes. So let's solve a problem, a very simple problem, just to apply this formula and determine if a fin should be added or not. Okay, so we need to compute the effectiveness of a longitudinal fin. So the problem is giving us the geometry, right, of the fin, because we need to calculate area and perimeter like we did last class, right, depending on the geometry, made of stainless steel. The fin length and thickness are 1.3 inches and 0.125 inches respectively. And the heat transfer coefficient, the H, is 3,500 BTU-hour feet square ranking. The thermal conductivity, or the K, for that particular stainless steel is 8.72 BTU-hour feet ranking. Should this fin be used? Well, we need to calculate effectiveness, right? So I calculated the fin parameter that, right, that is to HKT square root. So that gives me 278 feet minus 1. The perimeter for a longitudinal fin is 2L. The area is LT, length thickness. So the fin effectiveness is 0.69. So it's less than 1. So that means that we should not add the fin, right? So the last topic about steady conduction is the 2D steady conduction. Here, so when we are having heat transfer, so heat transfer between two isothermal surfaces, we use a modified Fourier equation. So two isothermal surfaces, steady state conduction, we use a modified Fourier. And that modified Fourier is pretty simple. It's going to be heat transfer rate between our two isothermal surfaces equals K, the thermal conductivity, times the shape factor times T hot minus T cold. Okay, so that is going to happen when we have heat transfer between two isothermal surfaces under steady state conduction. We need to modify our Fourier, and we are introducing this S, that is the shape factor. So Q, again, as always, and is small q, is heat transfer rate. K is the thermal conductivity that we get from tables, as always. S is the shape factor and depends on the geometry. Shape factor and conduction shape factor. And it's a small s, okay? Because later in this course, when we analyze unsteady conduction, we will have a big S, okay? So this conduction factor is a small s. And delta T, well, is just the driving force, right? So delta T, driving force for heat transfer. Driving force for heat transfer. Okay, so pretty easy this equation. And well, the only thing at this point that you don't know is from where to get the conduction shape factor, because the thermal conductivity, you know, we have tables for that, right? The delta T typically is given, and if it is not given, we can go and measure the temperature of the environment and our surface, right? So the only thing would be the shape factor, the conduction shape factor. And you have this table in your book. It's a 2-page or 3-page table, I don't remember, but it's table 2.3, conduction factor S for different systems. And here you have the equation, the modified Fourier, right, to calculate the heat transfer between two isothermal surfaces under steady state conduction. So for example, let's look at this table. You have here conduction through an homogeneous medium of thermal conductivity K between an isothermal surface and a sphere buried at a distance Z below the surface. So this is the formula for the shape factor. If you have, for example, a buried long cylinder, right? Here you have the shape factor. You have two cylinders at a distance L apart. Here you have the shape factor. So we go on, and you have all these for corners, for example, right? You have 0.15 delta X, that's a shape factor. So pretty easy. There's not much complication here. The most complicated problem that you can face is, for example, if I gave you, I don't know, a furnace in a cubical form. You need to, there's no cubics, there's not cubes in this table. So you need to assemble your cube. You need to add the walls, the corners, the edges, and build a cube. Okay? So it's like a Lego problem at the end. Okay, so I can do any shape with these shapes that you have in here. We can put together shapes. You add all the shape factors and put it in the modified Fourier. That's the most complicated thing you can face in this type of problems. Okay, that's a simple problem. So you can see how to use the table. Okay, So we have a 30-meter long, 10-centimeter diameter hot pipe of a district heating system is buried in the soil 50 centimeters below the ground surface. So you have here, right, the image. The average surface temperature of the pipe is 80, taking the surface of the earth to be 10 and the thermal conductivity of the soil at that location to be zero point 0.9 watts meter Kelvin, determine the rate heat loss from the pipe. So we are dealing with two isothermal surfaces, right? The first surface is the outside of the pipe itself, right? And the second one is the soil, right? So where heat transfer is occurring between these two temperatures. So we have the delta T, we have the K value for the thermal conductivity for the soil at that location, right? What would be missing? The shape factor, right? So we need to look into our table to see if we can find a shape factor for this particular geometry. So if you don't have your book available, we can check here in my presentation. And we have the conduction here. 2 pi L conduction through an homogeneous medium of thermal conductivity K between an isothermal surface and a horizontal cylinder of length L buried in its axis, a distance Z below the surface. We have that distance Z, right? So our shape factor is going to be 2 pi L divided by the cosine hyperbolic minus 1 times 2ZD, where C is that distance, as you can see here in this small drawing that you have in the table, right? Z is the distance buried, right? L is the length of our cylinder or pipe, right? So you have essentially everything to put into this equation. The diameter of the pipe, you already have it too. So with this one, calculate that S or shape factor, and then put it in the Fourier, modified Fourier. Modified Fourier is shape factor times K times delta T. We're just replacing the area by a shape factor, right? That describes our geometry. It's essentially what we are doing. So let's practice one more shape factor. So solve this one. You have the K, you have the temperatures, you have the length and the diameter of the both pipes. You just need to check a new shape factor because the geometry is changing. Now, we need to determine the rate of heat transfer between the two pipes. One pipe is at 70, the other one is at 15, right? So heat transfer under steady state conduction between two isothermal surfaces, the two surfaces of the pipes. So if you don't have the book handy, I can put the table here. So we have two pipes, right? This would be our two pipes. Geometry. Two long parallel cylinders. So in this case, the shape factor is going to be 2 pi cosine hyperbolic minus 1. L squared minus 1 minus R squared divided by 2R, where this R is radius 1 divided by radius 2, and the big L is the L, and little L is the distance that separates center from center of the two pipes divided by R2. So I got 52.2 watts. So with this 2D analysis, we conclude the steady conduction. Now we are going to evaluate unsteady conduction. So what we are going to cover in this lecture is lump heat capacity systems. That is a kind of idealization method to solve for unsteady state conduction. So the main learning objectives for this lecture would be to determine the difference between a steady and unsteady conduction. Determine if you can treat a system as a lump heat capacity system, that is kind of idealization, and use the lump heat capacity approach to calculate the required time to get to a certain temperature after a certain time. Because now we will have changes with time, right, in steady conduction. So let's first put side by side steady versus unsteady conduction. So in a steady conduction, the temperatures of the system do not change with time. We have spatial variations of the temperature, but the values are constant. We need spatial variations of the temperature because otherwise heat transfer won't take place, right? And as an example, take out this fin. Here, the temperature near the base of the fin is 80 Celsius, 70, 65, and the tip 56. So here near the base, all the time is going to be 80. Here at the tip is going to be at all times 56. That means we have spatial variations for heat transfer to occur, but the values are constant. Whereas in unsteady conduction, the temperatures of the system change with time. And this is generally caused because we change the surface conditions. The boundary conditions change with time for that particular object. And a pretty simple example is when we heat or cool objects. For example, when we boil an egg, right? We take out the egg from the fridge at 5 Celsius and we put it in boiling water at 100, right? Then the temperature is going to start increasing from the outer surface of the egg to the center, right? So we are suddenly changing the thermal environment of our object, okay? So when we suddenly apply these changes, right, that most probably means, or that means that we need to evaluate our problem as an unsteady state problem, okay? So one very simple way to evaluate unsteady state conduction problems is by analyzing our system as a lump heat capacity system. What is a lump heat capacity system? First of all, is an idealization, okay? It's a system in which the temperature is uniform throughout. And it can give us reasonable, accurate values for simple problems. And we will see that once we complete all the evaluation of all the different methods we have for evaluating unsteady state conduction, we are going to solve a problem with all the three methods, all the three main methods. And you will see how lump heat capacity system gives very fairly good results, and it's very simple to use. So to explain the lump heat capacity system, let's imagine that you have a small copper ball coming out of the oven, okay? So inside the oven, the ball, every single part of the ball was at 100 Celsius, for example. After 5 minutes, when you take it out from the oven, it's going to be every single, like I have here in this figure, every single point of that copper ball is going to be at 70 Celsius. So the temperature of the copper ball changed with time, but not with position during the heat transfer process. That means the temperatures of a lump heat capacity body can be taken as a function of time only. So we can talk about the temperature of the ball with no reference to a specific location, just with respect to time, right? At time zero, when it was inside the oven, every single part of the copper ball was at 100. The edge, the center, middle, every single part. When you take it out of the oven after 3-5 minutes, every single part is going to be at 70 Celsius. Okay, that's the idealization. That is the simplification, right? So only as a function of time, not position. Okay. So very important then that in lump heat capacity approach, we assume that the thermal conductivity K is infinite. And a way to approximate this is by considering that the resistance by conduction is much smaller than the resistance by convection, or S over K is much smaller than 1 over H, where S is the characteristic length. This is another S. Do not confuse it with the shape factor that we just checked. It is another S, and it's the characteristic length. So then, based on that, how we can define if we can treat a problem, an unsteady state conduction problem, as a long heat capacity system? Well, very simple. We can calculate a dimensionless parameter named the Biot number, okay? Where S is the characteristic length, K is the thermal conductivity, and H is the convective heat transfer coefficient. And based on what I established in the slide before, right here, or S over K being much smaller than 1 over H for a lump heat capacity system, what do you think? The Biot number should be a large number or a small number? Small number, right? And actually, it should be less than 0.1 to consider the use of lump heat capacity approach. So that will be our very first step with unsteady state conduction. Get your Biot number. If it is less than 0.1, go ahead and you can apply the lump heat capacity approach. If not, at this point, in this course, at this point, you cannot solve the problem, but later on we will see other methods, what happened with the Biot is larger than 0.1. So I have this S, right? So how we can get this S to get the Biot number, right? That would be the very first question. What is that S? Well, S is the characteristic length and depends on the geometry of the body we are evaluating. And as always, we will check plates, cylinders, and spheres. Okay, so the characteristic length for a plate is divided as B over A for the cylinder, and the sphere also volume over area. And if we cancel right H, Y, here we have that the characteristic length for a plate is only the length. Same thing with the cylinder, we cancel pi, 1R, the L, right? And the characteristic length for a long cylinder is going to be R over 2, the radius over 2. For a sphere, we do the same thing, and the characteristic length is going to be the radius over 3. So that's how you calculate the characteristic length for these three shapes. Again, for the plate, only L, the length. For the cylinder, R over 2, the radius over 2. And for a sphere, the radius over 3. That's how you calculate that characteristic length for getting the Biot number. So then let's go, now that we know when to treat a problem as a lump heat capacity system, and now that we know the idealization involved, let's develop the formulation associated to these systems. So in order to get the formulations to solve a system as a lump heat capacity approach, let's consider that we have this solid body, right? And that at time zero, this solid body is placed into a medium with temperature T surroundings or T infinity. The heat transfer takes place between the body and its environment with a heat transfer coefficient of H, right? So if we make a simple balance, energy out equals energy store, or the heat transfer into the body during a delta T equals the increase of energy of the body during delta T, we have this equation, right? Newton's cooling law equals rho v Cp dt over dt, where H is the heat transfer coefficient, rho is the density, V is the volume of the solid, Cp is the heat capacity, surface area, right, delta T. And very important, all this term, the rho VCP, is named the lump thermal capacitance of the solid. And as this term, it increases, as this term increases, the solid will respond more slowly to any changes. That's why that term is separated, okay? So again, as higher or as bigger this rho BCP, the body will respond slower to changes. So then we do as always, right, define our dimensionless temperature, where T here is the temperature at certain time, T infinity is the surroundings, we take derivative, rewrite equations, separate variables, integrate, defining theta I as T initial minus T surroundings. Finally, we have these two expressions, and I want that you take note of these two expressions. These are important. The first one is the expression to calculate the time to get to a certain temperature if we are considering that our system is behaving as a lump heat capacity system. The second one is the expression to find a particular temperature after a certain time, right? Again, when we are considering our system as a lump heat capacity system. Reminder, you have here a reminder of what every variable means in those equations. So these equations are the ones that are going to help us, again, to calculate the time to get at a certain temperature or to find a certain temperature after a certain time. Considering our system as an ideal system, as a lump heat capacity system. We need to get a long rod yellow brass with a diameter of 5.5 is suddenly exposed to a flow of minus 55 air, where the heat transfer coefficient is 120. If the initial temperature of the rod is 15 Celsius, what is the rod temperature after 2 minutes of exposure to the air? What would be the first step? You know that is an unsteady state problem, right? Because it's involving time. What happened with the temperature after 2 minutes, right? So it's an unsteady state problem. So first step could be get the Biot number to determine if we can treat it as a lump heat capacity system or not. If it is less than 0.1, you go ahead and treat it as a lump heat capacity system. You might need the K value. The K value for yellow brass is 116 watt meter Kelvin. So here is the data. You have the diameter of 5.5 centimeters. You have the T surroundings or T air minus 55. T initial of that rod is 15 Celsius. And H heat transfer coefficient of 120, and the K for yellow brass is 116 watt meter Kelvin. The specific heat for yellow brass is 377 joules kilogram Kelvin, and the density of the yellow brass is 8470 kilograms cubic meter. You want to know the temperature after 120 seconds. You are dealing with a cylinder, so the characteristic length is going to be R over 2, right? So first thing to do is to get the Biot number to determine if you can treat this system as a lump heat capacity system or not. If you see, we are dealing with a lump system, and I gave you the formulation, right, in previous slide to get the temperature after a certain time. So you just need to use that formula. So then we use the formula, right, that we have to get the temperature, the T. As always, I solve term by term before putting in the main formula. This is what I'm doing in here. I'm solving term by term, and I'm doing calculations per 1 meter length of cylinder.